Okay, good morning, everyone. Today we're going to continue our discussion on multiple linear regression, in particular, stepwise regression. So let's have a brief review of what we have discussed so far. We created an object called model one last time, and we used the linear model function where we regressed hourly wage on the variables that are available in the wage data set: education, experience, tenure, race, gender, civil status, and number of dependents. This can be written as by spelling out the predictors and then identifying that it's coming from the data from the wage data set, or just using this shortcut tilde and then dot. The dot here means include all the variables. Okay, so I'll just run this, and the summary function will give us the summary result of the model. So this is what we had last time. Okay, there's this call. This is the formula that we ask R to perform. We have residuals here, some descriptive statistics about the residuals. And then we have here the output, the regression output. Okay, so let's quickly review what this means. Education, 0.57. I'm just rounding off to the two decimal places. This tells us that for every 1 year, I'm using year because the dimension of education is yearly. For every 1 year increase in education, there's a corresponding $0.57 increase in hourly wage, ceteris paribus. And this this is statistically significant at 0.001. Okay, which means that this is coming from the null hypothesis. Okay, null hypothesis. Let's see if my okay. Hindi nagkaroon tong not working. Okay, I bought a digital pen from Lazada. So far, it's not working yet. So yung null hypothesis natin, di ba? Is that your beta education, oops, happened there, is equal to 0. Beta education is equal to 0. Okay? So that's what we're testing here, this parameter. And our conclusion is that we reject the null hypothesis that beta education is equal to 0. There's strong statistical reason to believe that the value of the beta parameter is a value other than 0. In fact, the average is 0.57. Okay, and it's far from 0. Okay, so that's what this this means. Okay. And then, class, how about for experience? For experience here, we're saying that if, assuming this is significant, for every 1 year increase in experience, there's a corresponding $0.02 increase in hourly wage, ceteris paribus. Okay. However, this one, the value of this one is not statistically significant. It is statistically significant at p value is equal to 0.10. But that's not the level of significance we're using. Our level of significance is 0.05. That's why it has only one dot here, this one class. 1.01. So this indicates our, again, our null hypothesis here is our beta experience. Beta experience is equal to 0. And since the p-value is 0.07 and it's greater than 0.05, our conclusion is we fail to reject the null hypothesis that your coefficient for experience is not equal to 0. Okay, Then you have tenure class. Again, this is statistically significant, and the value is 0.14 approximately. So we say that for every 1 year increase in tenure, there's a corresponding $0.14 increase in hourly wage, ceteris paribus. Okay. And then race white, we discussed this last time also. The value is around 0.11. How do we interpret this? Okay, we say that, okay, let me first. Okay, why is it not? Okay, ayaw ah. Okay, anyway. Okay, we're saying that 0.11, no? We're saying that on the average, white people receive $0.11 more than their non-white counterparts, ceteris paribus, assuming this is significant. Okay, assuming that's significant. So we interpret this categorical variable, this factor, the level, the level there is white. We interpret it in relation to the benchmark variable, which is non-white. Last time we learned that if a variable has, if a categorical variable, why isn't it appearing? Okay, problema annotate ko. Ayaw, there, one last time. So it doesn't show. Did I press something here? Anyway, close. I won't bother with the digital pen. Okay, gender. We were saying that race white is not significant. Okay. Then we have gender male, and we're saying that this would be interpreted in with reference to the in comparison with the reference variable, which is female. Okay, so we say that on the average, male counterparts, male employees receive $1.76 more than their female counterparts, ceteris paribus. And this is highly significant. Same thing with civil status, single, civil status. Okay, notice that it appended here the word single to mean that two things to mean that the one that's not appearing here is your reference. So married is your reference level. Okay. Single will now be interpreted in relation to the reference variable, which is married. So on the average, single employees receive around $0.46 less than their, less because this is a negative, less than their female, less than their married counterparts, ceteris paribus. However, we say that this is not statistically significant. Okay. So the null hypothesis here is that beta for civil status is also equal to 0. Okay. And we fail to reject that null hypothesis that beta beta civil status is not equal to 0. Okay, because this p-value is way greater than 0.05. Lastly, same also with the number of dependents. One increase in a dependent, hourly wage tends to increase by $0.15. Okay, ceteris paribus, and it's not significant also. Then we looked at the figures here. residual standard error class is 2.95, and it's just the equivalent to the standard error of your residuals. And we mentioned last time, class, that the model can generate the residuals. So if I use this function, names, okay, names of model one is the model that we generated, right? So if we run this, names, model one, okay. So these are the objects inside model one. So you have the coefficients, residuals. This is what we mean by residual standard error. It's just the standard deviation of your residuals. And we know that residuals can be computed by comparing the actual value of your wage. Okay, so this one, what is our actual value minus the predicted value or forecast value? The predicted value is obtained from the model itself. You can get it here, okay? Treated values, and you can also get the residuals. For example, if I do mod one dollar residuals, and let's just get the first 10 observations, for example. Get the head. Say first 10 observations. Control enter. There. It gives us the first 10 observations. And the model will also give us head and model one dollar. It will also give us the fitted values. There. And also, if I run this together, my mouse is something's wrong with my mouse. Okay, so let me just move that. Okay, we can generate this. Control enter. There you go. These are the first first 10 residuals. These are the first 10 fitted values. And this can easily be validated. If we go to our wage data, wage. So for example, the first observation, the first actual observation for hourly wage is 310. And then if I subtract that to the predicted value, this is the predicted value class. Okay, this is the fitted values. Control C, Control V. The difference between your actual and your predicted is here class 0.1823 there. Okay, so we can see that we were able to verify this. If I go, for example, to the second predicted value is this one, 12.8. And our actual value for the second observation is 3.24. So I'm going to subtract the actual value to the predicted value. So we're comparing what's the actual value and what's the predicted value. Control enter. That will be your residual. And if you take a look at the output here, the residual is 1.57406. Okay, exactly the same. Okay, let me pause for a while and try to see if I can confirm that you're able to follow so far. Kindly confirm, class, if what we have been discussing so far is clear. Very good. Very good. And you know, class, if you have any questions, please feel free to ask. Okay, so Moving on, class. Okay. We know, class, that what happens when we do regression. Okay. So this is our data. Now, how in the world is R able to create a regression model if you have here categorical variables? First, let's see what happens. We said last time that when we use categorical variables, not just any type of categorical variable, it should be there. All right, now I know. Okay, so for example, plus race. What really happens with this race variable or this gender variable? Let's look at this gender. We know that there are two levels here. You have female and male. And we said last time that what R will do is it will make this as your reference variable, okay? And this one will be your non-reference variable. So what exactly is happening here, class, when R creates a reference variable? Let me erase this. Okay. So here, to create a reference variable, what R will do is convert this gender variable into what we call a dummy variable. Okay, dummy. D-U-M-M-Y, dummy variable. Why is it called a dummy variable? Because there are no actual numerical variables here, numerical values. However, what R will do is that it will convert this into values. And how does it convert it into value? The reference variable, in this case, female, will be assigned a value of 0, okay? And the non-reference variable male will be given a value of 1. So for example, female here, this one is 0, okay? Another 0 here. Male here becomes 1. Male, male, etc. So all those males will become 1 and all those females will become 0. That's what we mean by dummy variable. Okay. Now take note, how many dummy variables are there? Okay. Before we answer that, for example, civil status. What happens to civil status? Civil status, you have single and married. We checked this last time using the levels function. So there are two levels. The one that appears alphabetically first is married. So therefore, married will be your reference variable. It will be given a value of 0. Okay. So what will happen here is that single will become 1, married is 0, single is 1, married is 0, 0, 0, 1, 1, 1, etc. So then the reference variables will be assigned a value of 0. The non-reference variables will be assigned a value of 1. Okay, so same thing here with race. Race, you have white and non-white. So the whites will get 1, the non-whites will get 0 because they're the reference variable. Okay. Now, what if, let's say you have this variable, let's say city. Okay, let's assume that there's this variable city here. Then you have, let's say, MK stands for Makati, ML stands for Manila, and SJ, let's say San Juan, and then let's say QC, okay, and then QC, and then SJ, and then Makati, and then Manila, etc. This is an example. Okay. So let's say you run levels and then there are 4 levels: Makati, Manila, San Juan, and Quezon City. So there are 4 levels. The question is, how do we create a dummy variable out of this? Okay. So how will the assigning of 0, 1, 1, 0 with how will how will that happen, plus? Okay, the way to go about that is okay, first determine the number of levels. How many levels are there? In this case, there are 4 levels: Makati, Manila, San Juan, and Quezon City. Okay, and then R will now introduce the number of levels minus 1 dummy variables. So that's the number of dummy variables that will be created. The number of levels minus 1. How many levels are there? 4 levels. Okay, and then we subtract 1 minus 1. So that will now be 3 dummy variables. So there are 3 dummy variables class. Okay, so how will that look like for the city? So you have here the city, and then so in that case, class, Makati, Manila, San Juan, and then Quezon City. Which will be the reference variable? Could you kindly chat, please? What will be a reference variable? Kindly chat, please. What is the reference variable? Makati. Okay. About the others, class? What's your answer? Makati, Makati, Makati. Okay. Why Makati, class? Why Makati? Same rule, same rule. It's the one that appears first alphabetically. Okay? Nasa unahan. Not unahan in order of appearance, class. Huh? Not the example I had a while ago where Makati was first. It's alphabetically. So even if the Makati is down at the bottom part, if it appears, if the data was sorted and that appears first, then that will be your reference variable. Okay? And it will get the value of 0. So how many dummy variables will be generated? There will be 3 dummy variables. 3. So what are these dummy variables? You'll have city Manila. They have Manila here. City San Juan. And then city, sorry for the, my digital pen is not working. Quezon City. So you'll have 3 dummy variables, class. 3 dummy variables. So, okay, still not working. How will that look like, class? How will that look like? So let's suppose our data is here. For example, this one is first observation is San Juan. Okay, having difficulty writing. Quezon City, and then Makati. Okay. I'll forget it. I'll just use, okay, let me open an Excel file just to illustrate this, class. Okay. Okay. Here. Mhm. So slow. Back here again. Apologies, class, for that. Okay, so back here, class. So suppose this is our data, Makati, and then another Makati, and then let's say the first one is Manila, and then San Juan here, and then Quezon City, Quezon City. Suppose these are the city addresses of the respondents. So how many dummy variables are we going to create? First, ask yourselves how many levels. There are 4 levels. Subtract 1. So therefore, we'll have 3 dummy variables. So what will be the dummy variables? Okay, first is what will be the reference level. It will be Makati. Therefore, the dummy variables will be your Manila, San Juan, and QC. This will be your dummy variables. 3. Okay, so let's plot this out. So if this is Manila, this will be 1, 0, 0. If this is Makati, this will be 0, 0, 0. Another Makati, 0, 0, 0. San Juan is 0, 1, 0. Quezon City is 0, 0, 1, 0, 0, 1. All right. So we have here, you're able to capture all the levels with just 3 dummy variables. Okay. So you don't need a dummy variable for Makati. Makati will be your reference variable. Is there anything wrong if we include Makati also as a dummy variable? Yes. Yes. If you include Makati here as another dummy variable, so we'll have here 0, 1, 1, right? Okay, so you have Makati as a dummy variable. You will have what we call a dummy variable truck. Dummy variable truck class, which means that your regression will not work because you will be having multicollinearity. Okay, this will lend to multicollinearity, and I'll explain this as we go along. But for now, class, okay, please be informed and please note that the number of dummy variables will be equal to the number of levels minus 1. Okay, you don't include the reference variable, reference level. So if Makati is the reference level, it will take on 0, 0, 0. And that will be understood by the model. Okay, all the 3 zeros there will pertain to Makati. So you're not including it in the dummy variable is because it's a reference variable. Okay, let me pause for a while, class, and ask you to please confirm if we're okay so far about the dummy variable, about the levels, how many dummy variables. Okay, thank you. So I'm waiting for the others to give their feedback. Again, English, if you if you have any questions, please feel free to ask questions. Okay, good. Thank you, everyone for your feedback. Okay, so let's now go here. Okay, now take note here, race. Okay, non-white and white. Therefore, non-white will be your reference variable. So what will be created will be race white. That will be your dummy variable. Okay, and here what will happen is that white will be all 1. So this will be 1, 1, 1, 1, 1. All your non-white will be 0. So you only need 1 dummy variable. If you have 2 levels, then it's 2 minus 1, 2 minus 1 dummy variable. So just 1. Okay, that's why for race there's only 1 dummy variable. For gender, 1 dummy variable. For civil status, 1 dummy variable. But if you have a variable that has, let's say, 5 levels, okay, for example, year levels, frosh, sophomore, junior, senior, graduating. Okay. In that case, you'll have 4 dummy variables, and the reference will be frosh, right? Sophomore, junior, senior, graduating. So it will be frosh. Frosh will be the reference. So you'll have 4 columns for sophomore, okay, sophomore, junior, senior, and graduating. And what will appear, okay, what will appear in your regression model, okay, Suppose you run that class, what will appear in your regression model is something like this. Okay. So there will be, for example, year level sophomore, year level junior, year level senior, year level grad. Okay. The 4 dummy variables will be there, except for the frosh. And then when you interpret each of them, it will be with reference to frosh. Okay, for example, on the average, sophomore students get blank, blank, blank compared to their frosh counterparts, etc. So again, because these are factors, these are categorical variables, okay, we we okay we it's run by converting them into dummy variables. All right, so let's go here, class. I would want you now to get, for example, the okay. Now my question is, R automatically identifies which is the reference variable. It alphabetizes your levels, and the one that appears first will be your reference variable. So for gender, okay, we have male, female. Female will be your reference. Male will be your non-reference. But if I want male to be the reference, what do I do? Can you change the reference? Yes, you can. But before we do that, let's first run this. I don't think I gave this to you, but you can easily run this, class. Just create another code chunk, and then let's get the class. Okay. So in your case, class, what's the class of gender? Could you please tell me if it's factor or character? In your case, is gender a factor variable class? Your response, please. What's the class of gender? Wage gender class. Character. Okay, character. Character. Okay, good. All right, because we changed this already a while ago. So, okay, how about, can you get the table? Can you get the distribution class? When you run table, wage, gender, what do you get? Again, please, another response. Okay, so it generates class. It creates a frequency distribution. What about getting the levels class? Thank you. Okay, good. So you were able to create a frequency distribution. However, for the levels, you're not getting anything. Okay, why? Why is that so, class? Because levels can only be used for, okay, also another one before we answer that level. Can you also get the contrasts right here, contrasts for gender, please, and tell me what do you get? Error for contrasts? What was the error message? Everyone, please. Contrasts. Contrasts, wage, dollar, gender. All right. Thank you, Marga. Okay, good. Thank you, Jocelyn. So I hope you got the same message, class. You cannot run contrasts, class, if you're only dealing with a character variable. So there's a need for us to convert. Okay. With table, it will work. However, with levels, it will not work if it's a character variable. So how do we convert class? Wage, gender. Okay. Alt minus. So let's convert wage gender into a factor. Okay. So that clearly it's for classification. Okay. Wage. And then we use as that factor, and then wage dollar gender. Okay. So can we do this class? And then after you run this, run class again and see if it was converted into a factor. I'll wait for your feedback class. I'll wait for your feedback if you were able to change the class of gender into a factor. Done. Okay, thank you. Okay, good. Thank all right. Thank you. Okay, good. So I hope that's clear, class. That if you check the class and then it's a character, you'll have to convert it into a factor in order to be able to run some of the functions like levels. So if you converted it into a factor and if you now run levels, that will now work. It will give us the levels. And so we know that R will alphabetically a female appears first. It will female will be assigned as your reference variable, and it will take on the value of 0, and male will be 1 in your dummy variable. And there will be only one dummy variable here. Now, can we verify if indeed, okay, if indeed female will be assigned the 0 value? Can you please check contrasts? If you if you check contrasts, class, what happens? What do you see, class? Was really the assignment 0 for the female and 1 for the male? Yeah, good. Thank you, Marga. How about the others? Yes. Thank you, Bea. The others too, please. Okay. Jay, thank you. Jocelyn, Carl, good. Good. Okay. So I hope everybody got this. Okay. So we checked. We were assuming last time that R will make the one that appears alphabetically first. It will give it the value of 0, and the other will be 1. Or if you have many levels, then the reference variable level will have 0, and the others will have 1 each. And you'll have L minus 1 dummy variables. So that's how it goes, class. That's why R is able to use factors as part of your regression. Okay, that's why we were able to get this. We were able to get these outputs, these regression outputs. Because even if race, gender, and civil status were all characters, they were converted into factors and they were used as part of the regression because they were assigned numbers, either 0 or 1. So they became quote unquote quantitative. So dummifying means you're converting your character into a quote unquote quantitative variable. All right, good. So we have this one. Okay. So here, why don't you try civil status, class? Try to see civil status, which is single and married. Let's see if the contrast is really married 0 and single as single as 1. You have to check first if civil status is factor. If not, then you'll have to convert that as a factor and then check the levels, check the contrasts. Okay, I'll give you a few seconds, class, to check what is the contrast for civil status. Is it what we were assuming? Married 0 and single as 1. Okay, any answer? Okay, Marga, married, zero, single one. Okay, good, thank you. Let's wait for the others and see if they got the same answer for the contrasts. Contrast, yes. Thank you, Jay. Yeah, you're correct. Jocelyn, thank you. Yeah, good. Okay, let's give a few more seconds to the others. Okay, good. I think all of you got it. Okay, thank you. Thank you, everyone. Now, my next question is it possible to change the leveling? I mean, can I use, if I want, for example, for gender, I want female to be, male to be the reference. Because as it stands right now, the default is that female is the reference variable. How do I now make it in such a way that male will now be your reference variable? Is that possible, class? Yes, it's possible. So let's take a look at this here. So we're going to use the relevel function. So we worked on gender a while ago. We said that gender has two levels. So the mere fact that this run class means that this is a factor because levels will not run if your variable is not a factor. Okay, now here class, I'm going to change by using the function relevel. And then I have to input this. Reference will be male. Okay, so take a look at that. So I'm I'll be overwriting wage gender, relevel it, relevel wage gender itself, and then I want now the reference to be male instead of the default female. Okay, and then run contrast again, class, and see see what will happen now. If you change the structure of your data, now your level is your reference level now is male instead of female. Okay, so I'll wait for your response, class. Your response should be what will now be your levels or your contrasts. So did male become one? Did male become zero and female become one? Let's see, class, your answers. Waiting for your response. Okay, Carl, thank you. Yeah, okay, good. Jocelyn, thank you. Let's give a few more seconds to the others. Cherry, thank you. Good. Good. Okay. Lisa. Okay. Okay, good. So I hope everybody's able to follow. Okay, so you can change it. You can change your you can change your reference. So what's the implication? So let's go back here, class. Let's go back here. If I'm going to change the reference, what will now appear here for gender is gender female already. Okay, why is that so? Why will this now be gender female? This will become gender female because the reference is now male, so male gets a 0 and your female gets a 1 in your dummy variable. So the result will now be based on female, the values for female, I'm sorry. The value will still be the same, but the sign will change. Okay, the sign will change now. It will still be significant, same level, and then the intercept may change. Okay, the intercept may change. Okay, so let's try this. We can work on the same model class here. It's still the same data wage, but however we change the structure of data. We wanted female to be the male to be the reference, so we changed it. We re-leveled it, and I'm going to run this. Control Enter. Okay, and then you should have this. Okay. Oh wait, what happened? Sorry, I didn't run class. Sorry, I didn't run the releveling. So let me run it first. Where was that? Okay, this one. I'll run this. So it's now male. That's the reference. And then I'm going to run the regression. And where's our regression? Where's that? Here. Okay, Control Enter. And then I'm sure in your case, we'll have the same class. Gender female this time. So when we interpret this, it will be on the average, female employees receive $1.76 less than their male counterparts, ceteris paribus. And you notice there's a difference in the intercept now. Okay. The intercept would probably change, but the other values will be the same unless you're changing it will remain the same for the categorical variables. For the factors, it will be just a negation. Okay? Now, before we leave this class, let me ask you, what's the meaning of intercept? Can you please, I'll give you 1 minute to please write in the chat box, okay, and address it to me. I'll give you 1 minute to interpret. What's the meaning of intercept there? How do we interpret the intercept? Negative 1.63 in this case. I'll give you a minute to write, please, and direct your answer to me. I'd like to see how you're interpreting the intercept. Okay. All right. So let me see. Let me just so may mga answers tayo dito. Okay. Okay. Thank you, Jocelyn. So Jocelyn gave the right answer, but we'll expound on that. Jocelyn, can you please unmute and then read your answer?
Hello po, sir. Am I audible
Yes.
po?
Yeah, audible ka. Yes.
Intercept is the value of your dependent variable H or wage when all your predictors are zero.
Correct. Okay. So if you're going to shortcut it, negative 1.63, that's the average hourly wage of an employee with zero values of those predictors. Now, of course, class, it doesn't have any practical or significant meaning. Why? Because nobody can have a negative 1.63 hourly wage, because that would mean the individual, the employee, paying the company. So we don't put any physical or practical interpretation of that. However, we just put some theoretical uh, implication. So what's that implication? On the average, a person with uh, zero education, zero experience, zero tenure, no number of dependents, who is non-white, who is male, and who is married receives on the average negative $1.63 hourly wage. Okay, let me repeat that. On the average, an employee with zero education, zero experience, zero tenure, zero number of dependents, who is male, who is non-white, who is male, and who is married receives negative 1.63 negative 1.63, okay, dollars of hourly wage. Okay. I hope you got it. Let me pause for a while. Maybe you're writing it. I'll allow you to write. And I'm sure you might have questions about that interpretation. Okay. I was assuming, class, that everything here is significant. Okay. Let's assume first that everything here is significant. Because if it's not significant, then the civil status or number of dependents will not matter because they're not significant. Okay, I'll give you a few seconds. If you have any questions, okay, please please write it now. If it's clear to you, please write yes. I'm expecting some questions, class. No questions? No clarifications? No request for me to repeat the explanation?
None po, sir.
None, wow. Buka kagad, good. Baka may questions kayo? Anybody wants me to repeat the explanation? And so far, okay. All right, here there's a question. Okay, let me repeat. There's a request for me to repeat. Okay, so what's the meaning of negative 1.63? Let me explain. Negative 1.63, which is the intercept, theoretically we say that this is the average value, average hourly wage, if all your predictors are equal to 0. So for the quantitative variables, that's highly, that's practically self-explanatory. 0 years of education. Okay, so let me repeat. A person with an hourly wage of negative 1.63 is an employee with 0 education, no experience, no tenure. So lahat 0, no? No number of dependents. And who is, okay, who is non-white. Why non-white? Because remember, the reference value here, the reference level is non-white. And you can see that immediately. It's white here, right? Which means white got the number 1, non-white got the number 0. So if this is 0, if we're going to let this 0 be 0, then non-white is 0, class, right? White is 1, non-white is 0. So race white is equal to 0 means it's non-white. So that's why I said who is non-white, who is male, in this case, male, and then who is married. Okay, because those are your reference variables. And if it's a reference variable, the value here will be 0. Okay, so that's why I said who is non-white, who is male, who is married. Okay. Now, if I ask you, for example, what will be the average, okay? Average hourly wage of a person who has 1 year of education, 1 year of experience, 1 year of tenure, okay, who is male, who is white, okay, who is white, the person is white, then he is, that person is white, he is also a male, he is also single, okay? So this is our question. The person is male, He's white, single, white, male, and single. And who has 1 year of education, one experience, one tenure, and one number of dependent. So what will be the average? What will be the average hourly wage? So what will happen, class, is that 0.57 will appear because 1 year of education, 1 year times 0.57, right, class? So this will be 0.057, correct? Plus 1 year of experience. Again, assuming that all of these are significant. So there will be 0.02, 0.022. That will also appear. Okay. 1 year of tenure plus 0.138, 0.138. Okay. Plus who is male. So who is white. So if it's white, class, then this will appear. Plus 0.11. 0.11, right? 0.11. Because this is white, class. And then who is who is male? So if it's male, class, then this will be zeroed out. Okay. This will not appear. And then who is single? Single, this will appear minus 0.147. Let me just minus 0.1.4. Sorry, mali. 0.46, 0.46, and then plus one dependent, 0.147. Okay. And then you have to add the intercept, minus 1.63. So the intercept will be included. All the factors here will be added, class. So this is a person who has 1 year education, 1 year experience, 1 year tenure, one dependent, who is white, who is male, and then who is single. Okay. The male, white, the male class will be 0. Okay. So what will be the average hourly wage of that person? Control Enter. It will be negative 1.61. Okay. It's small because the intercept is very small. Okay. The others are also quite quite small. Okay. But of course, if we add, for example, it's now 10 years. Okay, 10 years education, 8 years experience, etc., then this will now be changing. Okay, let me pause for a while, class. Is that clear, class? Is the interpretation of the computation of the average hourly wage clear, class? So this will have a bearing, class, this one. Okay, so if it's white, then 0.10 will appear. If it's female, then negative 1.76 will be included. If it's married, then this one will not be included. Okay, so that's how you go about it. Okay. Okay, questions, class? Kindly please confirm so that we can move forward. We have a lot to cover still. I want us to be on the same page as the other section, please. Clear? Okay, good. So you just have to play around with this one, class. Okay, if it's non-white, then this will not be a factor. If it's white, then you have to include this. Female, include this in the computation. Male, do not include. Single, include this. Non-single, married, do not include this. Okay. Now I'd like to let's go back to I'd like to gender, the gender that I used a while ago, the level. I'll put back the okay, where's that? Might get confused here. I'll just put back, class, the releveling here. I'll make it female again. Okay. Back to our original model. I'll change it once again to female and then run this. And then again, this is female 0. And then run once again our regression model here. So this will revert back to the first one that we had. Okay. All right. Then let's continue, class. We said last time that we don't stop here. Okay. We don't stop here because we perform stepwise regression. So in stepwise regression, what we did was to take a look at our model, and there are some non-significant predictors yet. So we just can't leave that as is. So what we do is stepwise. This is stepwise backward because we started with the full model, and then we will go backward and remove variables one at a time. And then we said that the candidate is the one with the least t-value, t-stat, and that's raised 0.257. Okay. You don't look at the negative class. Algebraically, this is the lowest, negative 1.556. And the lowest t-value will be non-significant, definitely. Okay, of course, class, if these are all significant, then you're done with the model. That's it. That's your final model. So for this one, this one t-value is 0.257. Therefore, our living variable is raised. So we created a new model, class. Our model is model 2 last time. We did that. So where's that? Here. Model number 2, our living variable is race. So we now have 6 variables here. Okay, education, experience, tenure, without race. So when we run this class, okay, we did this last time already. So I'm just quickly going over it, class. We get this, class. Okay, and by the way, sorry, I forgot to review this one, class. What's the meaning of degree of freedom 1, degree of freedom 2? Degree of freedom 1 will be the number of your predictors. So for model 1, we have 7 predictors. Degree of freedom 2 is your n minus k minus 1, where n is your number of observations, n minus k minus 1. This is your df2. Degree of freedom 2. N is number of observations, 526. K is your number of predictors, which is your df1, 7, and minus 1, 518. That's where we got this. Okay. And why do we need this? We need this especially before if people use tables in order to get statistics. Okay. But now we're using R. So, but it's important to know these things. And in fact, we can create a function with F, supply degree of freedom 1, degree of freedom 2 to get the p-value. We can do that, but let's not do that now. Okay. And then we said that the adjusted R squared is very important because it tells us the amount, the proportion of the variability of your dependent variable that can be explained by your model. Our model here is model 1, and it can explain 36.19% of the variation of the variability of your hourly wage. How about the 64% or so? Then perhaps other variables, if they're also introduced, could improve this adjusted R squared. We don't use the multiple R squared because this is biased to higher number of predictors. So if you have 100 predictors, it will always have a higher multiple R squared compared to one with 80 predictors. So that's why we don't use this. Rather, we use this because the adjusted R squared will penalize the model for adding more variables. That's why oftentimes, okay, if we compare based on multiple R squared, the one with more predictors will always win, but not with the adjusted R squared. Okay. Again, this is a better metric because it penalizes the model for getting in more predictors, which might not be necessary. All right. And then p-value here, practically 0. So the null hypothesis is we're checking whether education is equal to experience is equal to all the 7 variables, and they're all equal to ... if they're all equal to 0. Okay, by this we mean that there are no significant predictors. Okay, and because of the very low p-value, we reject this. we reject this null hypothesis. There are strong reason to believe that at least one of the predictors is significant. It's not equal to 0. Okay? So now let's go back to to the model number 2, and we'll quickly go through this class because we have discussed this previously, and I want us to be on the same page as the other section. All right, so you notice that the adjusted R squared went up. Definitely the multiple R squared will go down because this has only 6 predictors. But the adjusted went up, 36.3619, I think, 3631. This is better in terms of adjusted R squared. But this is not at the end. We'll have to, we're doing stepwise. We have to remove the lowest T value, which is civil status, so this one. Absolute value, 1.582. Sorry, 1.33. My bad, class. 1.33. So this should be your living variable because this is the lowest absolute value of your T value, and it's not significant. All right, so living variable now is, by the way, sorry, I failed to do this. We have to check, class, if indeed model number 1 with 7 predictors, if model number 2 with 6 predictors is better than model number 1. So by way of review, class, and I'm going through this very quickly, plus the null hypothesis here, we can state it 2 ways. The living variable was, what was the living variable? Race, right? Beta, the parameter for race, is equal to 0. That was what we were testing. Or another way to say this is that the restricted model, restricted meaning lesser predictors, is better than your unrestricted. So this is our null hypothesis. Okay, so we run this ANOVA, this analysis of variance, and okay, if I run this ANOVA, what do we see? The p-value is 0.79, much higher than 0.05. Therefore, conclusion is failure to reject the null hypothesis. We fail to reject the null hypothesis that the restricted model is better than the unrestricted, or that beta race is equal to 0. So there's strong statistical reason to believe that your coefficient for race is equal to 0. Okay, and that your restricted model is better. So there's no use including race as a predictor. Okay, because statistically it's better not to include that. All right, so with that, class, we can now, I'm doing this, okay, I'm looking at the time. Annotate, sorry, let me just remove that. Okay, so now what's next, class? We looked at the model, and number of dependents is the least in t-stat, so that one will go away. Class, leaving variable number of dependents, so we now have only 5 predictors here: education, experience, tenure, no more number of dependents, no more race. Okay, so we create this model number 3, and this is what we got, class. Okay, notice the adjusted R squared went down, 36.21. It doesn't mean that if you always exclude or remove a variable, the adjusted R squared will automatically go up. Sometimes it will not, okay? Because this is based on a computation. However, even if it did not go up, okay, it's lower than model number 2. That's not the necessary acid test, okay? So we have to look at the predictors, and you can see that there are still 2 insignificant predictors: experience and civil status. Now, civil status is significant at 10%, but experience is not. Okay, so definitely based on the t-value, this will be the one to go. Okay, negative 1.956 absolute value. Okay, the lowest is 1.558. Okay, absolute value only, class. Don't consider the negative sign. All right, so we again check, class. Okay, does it make sense to include number of dependents? So we do ANOVA for model number 2 and model number 3, and it turns out, class, that the I'm going through this class because this was supposed to be your assignment. The p-value is 0.18. Therefore, we fail to reject the null hypothesis that beta number of dependents is equal to 0. So it doesn't make sense to include number of dependents, okay, because it's statistically equal to 0. So no effect. Okay, therefore, model here, model number 3 is the better model. Okay, so what happens next? The lone, okay, after we run the last model class, okay, what happened? Here, experience class, sorry. Experience, leaving variable experience. So no experience here. We run the model class. And it turns out that all the predictors are significant. So this will be our final model. And let's just check, compare model 3 and model 4. Model 3 has experience with it here. Model 4, we remove experience. And the p-value class is 0.1198. So we fail to reject the null hypothesis that model number 4 is better. Okay, so, all right. Okay, let me pause for a while, class. We have some 13 to 15 minutes. Okay, any questions, class? Any questions with this quick discussion? As I said, you were supposed to run this up to the end, so I'm discussing it. I'm discussing it faster than usual. Okay, any questions? Anything you'd like me to repeat there? So your model now, class, will be hourly wage is equal to negative 2.16 plus 0.53 times education plus 0.15 times tenure plus 1.7 times gender minus 0.68 times civil status plus E epsilon sub I, your residual, your error term. So we have 4 predictors out of the 7, 3 were removed. Okay, so what would have happened, class, if we at the initial step, class, where was our first regression class? So in our first regression, only 3 were statistically significant: education, tenure, and gender male. Okay, experience was not. So had we stopped here, class, our model would have been just 3 variables: education, tenure, and gender male. However, when we did the stepwise regression, it turned out that there were 4, including the civil status. Okay, here, civil status was included as part of our final model class. Okay, sorry, where's that? One last, here, class, here. Okay. So there's a reason why we make use of stepwise regression as compared to just in the first run, just remove all the insignificant predictors. Okay, because some of the predictors, class, might be competing in explaining your, remember that there are some that are a bit mediumly correlated. Okay. All right. Can I chat, please, class, if it's clear so far? I'd like to have your feedback, class. Any questions, clarifications? We go to the last part. Okay, good. Good. Thank you. Thank you. Okay. Now, for the last parts of our multiple linear regression, we have stepwise. We'll finalize our discussion on stepwise. I will not be able to finish everything today, but we'll be discussing that on Monday. And then with, with that will be your interactions. And then the last topic will be your diagnostics. All right, so please go to your RMD file that you copied, class. Okay, and please make sure this have been loaded, especially OLSRR. This is what we're going to use. Okay, OLSRR. And then we have already imported wage, so let's not do that. So we'll go here, class. Forward regression. In the interest of time, I'm going to share this with you. Control C. In the chat box, please copy this. Okay, we already did stepwise regression here, class. We did this here, stepwise regression. However, what we did was manual. So imagine if you have 20 predictors and you're going to do stepwise regression, you're going to do it one step at a time. Okay, and that can be very, very difficult, can be very cumbersome. So there's a package in our OLSRR which can automate everything for us. It can show you how the stepwise backward regression was created or forward. Okay, so let's start first with this forward regression. Forward regression plus forward stepwise regression is different from backward stepwise regression. When we do forward stepwise regression, what happens is you start with nothing. You don't have a predictor, just the average class, just the intercept. Okay. And then what R will do is it will choose. So usually it will be the one with the highest correlation. So it will enter. So if it's leaving for LEAVING, leaving for backward, it will be entering for forward. So it will keep on increasing or adding on variables. So first here, we're going to recreate the model. I'm just going to name it model. It's the same LM function of all our predictors. Data is equal to age. So let's run this. And of course, you'll have the same output. Okay. So this will be model now. Model. We will now have the model data. Here, model. It's the same as your mod 1. Okay. And then here, take a look at this class. This one is from OLSRR. Okay. And this function OLS stepwise forward and then P. It means that this uses the forward stepwise regression and it uses the p-value method. There are two methods that's used in stepwise regression. You have the p-value method and you have the AIC method. For the p-value method, you use a particular level of significance, let's say 0.05, in order to determine if a variable will enter or leave the model. So here, we're going to use step forward, and then we're going to do it for our model, which is this one. And then the parameter is, since this is P method, we have to define what the significant level of significance is. So we're using 0.05. Okay, and then putting curly brackets here, class, will print automatically the result. Okay, so let's do this, Control Enter. All right. And you can see here, okay, so let me see. I'll first, sorry, I'll just, let me decrease a bit the appearance class. I'm sorry about this. I'll make it 16 just to make sure that it fits the, okay. And I'll run this again. Control Enter. There. That still doesn't fit. But anyway, so what do we have here, class? What do you have here? Stepwise regression. What happened here, class? Stepwise summary. So first is the base model. So you have the base model where you don't have any predictor. Okay, you don't have any predictor. And then what next? The next is you inserted education. Okay. And then you inserted tenure. And then gender, civil status, experience, number of dependents. I think, do you get the same result, class? I'm having a syntax error here. OLS step forward P. Let me check this class because this is supposed to be using the p-value that I'm getting. So, okay, let me just check this function. This should be p-value, but I'm surprised why the values that are inserted. Okay. All right. And besides, it's time, class. Okay. So let me just end here, class. So for next week, we're going to discuss, class, the text that I sent to you. So we're going to use OLSRR to do forward stepwise, backward stepwise, and both. And at the end, we're going to look at, it will give us the best model, whether it's forward or backward. Okay, so this is a pretty important function. And then after this, we're going to do interaction. All right. So let me